Welcome back to the afternoon session. And this afternoon we'll have two talks on slightly more plasmonic, so chemical topics. We'll be talking about plasmon-driven photocatalysis, and after that we'll move on to the poster sessions as well. Okay, so we have two speakers, very exciting talks, and we'll kick off with Ruben Hamans from the Vrije Universiteit Amsterdam, who will be talking about how we can use super resolution spectroscopy for real-time monitoring of plasmon-driven photocatalytic reactions. So Ruben, do you want to load your presentation up?
Yes, let me see. Here we go. I think this should be fine, right?
Yes.
Okay, nice. Yeah, thanks for the introduction. Actually, when my abstract got accepted, I didn't realize that I made it to such a short list of speakers. So I do really feel honored that I'm given the opportunity to present my results. And I should also mention that indeed, also according to the program, our group is now at the Vrije Universiteit in Amsterdam. But I should also give due credits to the Dutch Institute for Fundamental Energy Research in Eindhoven, which is where we were previously. And also most of the results that I'm showing today have actually been performed there. So what I want to talk to you about today indeed is fluorescence microscopy, and more specifically how we can use this to map catalytic reactions at the single turnover rate on individual plasmonic particles. And of course, normally now I would start with a lengthy introduction on what the word plasmon means, but luckily for this audience, I can skip that part. So I will just only briefly mention that there's of course a few mechanisms by which plasmons can enhance chemical reactions. And first of all is of course the fact that metal particles are able to focus light right at the surface of the particle, so they can generate plasmonic near fields. And then of course, if you have some sort of photo-driven process that happens right at the surface, this can be accelerated. And then secondly, of course, plasmonic particles are good absorbers, and during the absorption of light, you can generate highly energetic electrons and holes, which you can use, for example, to drive redox reactions. But these carriers can also further decay and heat up the particle, which is of course another way in which you can accelerate chemical reactions. And I believe that this will be discussed extensively in the next talk, the one after mine. So now, of course, the question becomes, how do you characterize these processes? And you can either choose to characterize the optical properties of your catalysts, or you can choose to characterize the reactants and the products. Now, if you choose to characterize the optical properties of your catalysts, I think the most straightforward thing to do would be to take UV-vis transmission, so to just measure the extinction of your nanorods. So for example, what you can do is have a solution of plasmonic catalysts, and you put them in some sort of reactive environment and then measure the extinction of the rods as a certain chemical reaction goes on. And this is something that we have done in our group, for example, for gold nanorods that are in a growth solution for a silver shell. And then you can measure the extinction of your nanorod solution as a function of time, and then say something about how the growth of this silver shell has progressed over time. And then if you do this in a temperature controlled environment and you vary your illumination geometry, you can say something useful about the process that is actually happening. And in this case, we found that actually the reaction was driven by interband hot holes. Now, of course, the upside to these kinds of measurements is that the measurement itself is relatively straightforward, even though the interpretation of the data can still be quite intense. But then, of course, the downside is that you're measuring on many particles at the same time. And obviously, there will always be some sort of heterogeneity from particle to particle. And this can either be in the distribution of the nanoparticle sizes, or maybe a distribution in active sites, or maybe the catalyst will restructure during the process. And also you cannot control the orientation of your particle with respect to polarization, especially if you're working in a liquid. So it would be much more ideal to do these measurements at the single particle level. And in that case, you can still choose to measure the optical properties of your catalyst, for example, using dark field spectroscopy. So then you simply have a white light source that excites your substrate at a high angle, and then in the reflection, you filter out direct reflections and you only look at diffuse reflections. So you work against a dark background and you only see the scattering from individual plasmonic nanoparticles. And then you can guide this light toward a spectrometer and, for example, measure the scattering spectrum. And this we have also used, for example, to grow semiconducting shells around individual particles, or also to track the restructuring of individual catalysts during a catalytic process. But these are all experiments done by my colleagues, and my project is slightly different. So in my case, I do not look at the optical properties of the plasmonic particles, but I look at reaction products. And more specifically, I look at the following chemical reaction. This is a reduction catalyzed by gold from a molecule called resazurin into a molecule called resorphin. What is nice about this chemical reaction is that it turns a molecule that is not fluorescent into a molecule that is fluorescent. So then if I allow this reaction to proceed inside a fluorescence microscope, every time a chemical reaction occurs, I should see a burst of fluorescence. So how do we do this in practice? Well, first we start out by synthesizing our catalysts. And in our case, I use gold nanorods. And as you can see in the TEM image, they're coated with a shell here. And I want to spend a few moments explaining why the shell is necessary. So here I've labeled it MSiO2, which means mesoporous silica. And as I mentioned before, we want to generate fluorescent products that are generated close to a gold surface, well, at or close to a gold surface. But we also know that metal surfaces are good at quenching fluorescence. So if a fluorescent molecule is very close to this gold nanorod, there's actually quite a high probability that I wouldn't detect the fluorescence in the far field using a microscope objective. But then if I wouldn't have a shell and the molecule desorbs, that means it will be in solution and it will be in Brownian motion, which means that on the timescales that we use, it moves really, really quickly because we typically use integration times of at least a few tens of milliseconds. In my case, I use 100 milliseconds. So then, of course, that means that the molecule needs to stay in the same position for that amount of time in order to get a well-defined image. And clearly, when the molecule is Brownian motion, it is in Brownian motion, that wouldn't be the case. So we need a sort of intermediate stage where the molecule can still reach the gold surface to convert, but at the same time, it needs to be slowed down. So in this case, it will stochastically absorb inside this mesoporous silica shell, which then allows us to detect it using a fluorescence microscope. So after synthesizing these catalysts, I will drop cast them on a glass cover slip. And then this cover slip we build into a nice flow cell so that we can continuously supply reactants, which then allows us to perform measurements over long periods of time. And then we have a microscope objective from the bottom, which does laser excitation in a total and tonal reflection geometry, so that we're only sensitive to what happens right at the surface. And then products will be generated, and these the fluorescence of which we collect using the same microscope objective. So in reality, this looks something like this. So we have our system of two cover slips nicely put together into this sample holder. And then we have tubing from the side that allows for the flow of reactants. And then we have the microscope objective from the bottom that does the excitation and also collects the emission. So of course, when I drop cast my nanoparticles, I do this at a very dilute concentration so that I can quite easily interrogate them individually, as you can see from the transmitted white light image on the left-hand side here. But then when I look at fluorescence, every time a product is generated, a particle will light up. And then every time the product desorbs and exits the shell again, the particle will turn dark again. So now this is, of course, already quite a powerful system because this means that we can now start interrogating the catalytic properties of individual particles. But now, of course, the question is if we can gain any mechanistic understanding of the process that is happening. And for that, we first need to know the ways in which resazurin can convert into resorphin. And this can actually happen in two ways. So the first pathway is a reductive deoxygenation. And this is catalyzed by gold and also requires hydroxylamine to be present. This is the NH2OH, and that acts as an external reducing agent. And then there's a second pathway, which is a photo-driven disproportionation. And you see that's the one on the bottom and does not require an external reducing agent, but it requires light as an input. So that would be a photo-driven process. And then in order to distinguish between these two pathways, what we did is we simply measured the turnover rate, so the number of detections per second, as a function of power both in the presence and in the absence of this external reducing agent. And you see here that we find that in both cases, the turnover rate increases quadratically as a function of power, which is actually what we suspect for both pathways. But you also see that the turnover rate doesn't change if we include or exclude the external reducing agent. So that, of course, suggests that in our case, this photo-driven mechanism is the dominant pathway. And of course, this is quite an interesting observation because, of course, if the reaction is photo-driven, then that would suggest that the plasmonic near fields are the driving force behind this chemical reaction. So that then also suggests that there should exist some sort of spatial correlation between the positions where you have high electric field and the positions where you observe high catalytic activity. So what we are going to do is we're going to simulate the electric field around the nanorods and then see if the positions where we observe hotspots are also the positions where we observe high catalytic activity. So for these simulations, we use a finite difference time domain method, and we simulate a single gold rod. We simulate a single gold rod on top of a cover slip, and then we inject a p-polarized field at a high angle, again, because we're using total internal reflection. And then we're monitoring the field at the bottom of the nanorod, which is actually where we observe the highest field enhancements. And then when the rod is oriented along the propagation direction of the field, we find that the field enhancement on the rightmost tip is significantly higher than the field enhancement on the leftmost tip. On the other hand, if the particle is oriented perpendicular to the propagation direction of the field, you see that the field enhancement between the two tips is equal. So now, of course, the question becomes, do we also observe this experimentally? So does the reactivity ratio between the two nanorod tips change as the orientation of the particle changes? Now, if you want to make this comparison, you see that you immediately run into some resolution issues because you see that the distance between these two nanorod tips is actually very small, whereas the features that we see experimentally are actually quite large. So here you see an example on the left-hand side. You see a field of view of multiple catalytic reactions happening at the same time. Then if we zoom into one, you see that the emission pattern from one of these fluorescent products is actually quite large because this is simply limited by diffraction. And clearly this is much larger than the size of one gold nanorod. But luckily we can do better than this because we can take this data and fit it to a two-dimensional Gaussian. And then the middle of the fit becomes the position of the molecule. And clearly this is something that we can determine with an accuracy that's much larger than just the size of the Gaussian itself. And in fact, if you do the calculation, you find that it roughly scales with the width of this point spread function divided by the square root of the number of photons that you detect. And in our case, that resolution is roughly 30 nanometers. So what we are effectively doing is this. We have a gold nanorod with on top of it all of these fluorescent bursts. But because these bursts are separated in time, we can take each one of them individually and fit them to a two-dimensional Gaussian to see exactly where did the catalytic reaction happen. And that then allows us to make these two-dimensional maps of catalytic activity. So here I'm just showing 4 examples, but of course I have one for each particle that was in the field of view. And then this is what we want to compare to our simulations. And in order to do that somewhat quantitatively, we decided to look at the angular distribution of events rather than just the XY coordinates. So if I take the example on the right-hand side here, you see that the distribution consists of, the angular distribution consists of 2 peaks, which of course correspond to the two tips of the nanorod. And then what I do is I take this data and fit it to a function that also has 2 peaks. And that then allows me to extract several parameters. First of all, the orientation of the particle, theta 0 here, and the amplitude of these 2 peaks, so A1 and A2, which are the reactivity of those 2 tips. And then the question becomes, does the reactivity ratio, so the ratio A1 over A2, does that in any way depend on the orientation of the particle? So that is what I'm plotting here. So you can already see some sort of trend. So here each point is an average over every particle that happens to have its orientation at that angle. And then the quantity that I'm plotting is the experimental ratio between the tip reactivity. So the ratio between these amplitudes A1 and A2. And then the question is, how does this compare to our simulation? So that would be the line here. So here the line is the simulated ratio between the electric field on the tips. So the average field enhancement on the one tip divided by the average field enhancement on the other tip. And of course, here the striking feature is that in both cases, you go from values that are higher than 1 for angles below pi/2 to values that are lower than 1 for angles above pi/2. And we can actually make this agreement a bit better if we only consider the electric field in the outermost part of the silica shell, because as mentioned before, molecules that are close to the gold surface, their fluorescence can be quenched and we don't observe their fluorescence in the far field. So we do in fact find that there's a very good correlation between the positions where you observe high electric field and the positions where you observe high catalytic activity. So now before I finish, I should mention that these results are now published in Nano Letters, which of course makes us very happy. And that now we are working on a similar but also different system where hopefully we can accelerate the chemical reactivity using plasmonic hot charge carriers rather than plasmonic near fields. And then hopefully using this system, we can learn something new about plasmonic chemistry. So I would say stay tuned. Thank you very much.
Thank you very much, Ruben. Does anybody have any questions? Yes, I'm not sure where I would actually know of people asking questions.
Yeah, the chat looks pretty empty, unfortunately.
Right, okay, well, or maybe I could ask one. In your experiment, you measure all of the data in real time, but then the calculation of the angle for the particle position and interpretation of that, does that happen in real life, or do you do post-process afterwards?
Yeah, we do a lot of post-processing. So because of course the one sensor of one camera is pretty large, so the amount of data that we collect is pretty intense. These are experiments that last for 10,000s of frames, where one frame is already 2 megabytes of data. So typically after the experiment, I will run all the two-dimensional fitting of all these emission patterns overnight, and then the rest of the analysis is all done later.
Okay. No. And then there's
so during the experiment, I have no clue what's going on.
Okay, fair enough. Anton, do you have a question?
Yes. Thank you for an interesting talk. I was just wondering if it's not obvious only for me, why is the reaction rate scales as quadratically as a function of power?
Yeah, that's a good question. That's because the mechanism, unfortunately, in our case, is quite complicated and also quite hard to explain. But it happens in 2 steps. And in the first step, you have 2 resuscitant molecules in the photoexcited state that disproportionate. So that means that one goes into a 1 electron reduced state and the other goes in a 1 electron oxidized state. And because you start with 2 photoexcited resuscitant molecules that need to be in the same position, you get a second order dependence.
So you're effectively absorbing 2 photons, right?
Yeah, exactly.
Yeah. Okay. Thanks.
And the same actually goes for the reductive deoxygenation reaction, I should add. But in that case, it can be either photoexcited resuscitant molecules that enhance the rate, or it can be plasmonic hot electrons. It's still a bit unclear, actually.
Any other questions?
I have one question, Sash. Thanks, Ruben. Really nice. So I was wondering if you have noticed that the reactivity of the particles change in time. So how stable is your silica mesoporous coating on the nanoparticles?
Yeah, so that's a very good point. So I should mention that after synthesis of the mesoporous silica, we keep the rods in ethanol, because in water the silica will disappear after a while. And we do see that indeed and you can, no, I don't have the data here, unfortunately, but you see that a bit.
But
the reactivity will go down as a function of time. So for example, the black spot here is the one that we measured at the start of the experiment, and the black spot here is the one at the end.
But the
and this
reaction,
will be like 2
it's
or
in
3
water.
hours. Come again?
The reaction itself, it's in water.
Yes.
Okay, so you store it in ethanol, but then you change into water for the experiments.
Yeah, exactly. Yeah, we keep it in ethanol for as long as we can, and then of course we have to go to water for the final experiment. Yeah.
And how long is that in time? Like from these 2 points, for example. So how long it takes?
I think, yeah, in total maybe like 3 or 4 hours, because we typically start with a bit of photo bleaching to make sure that everything is clean before we really start the experiment. So by the end, the rods will be in water for, I would say, 4 hours.
Cool. Thank you.
Cheers.
Right. Thank you very much, Ruben. I'm afraid we have to move on, but if people do have questions, then please come to the roundtable discussion later, and we can interrogate Ruben a little bit more about the very, very cool experiment that he did. All right, so let's move on to Wouter Koopman, who's from University of Potsdam, and he will be talking about the importance of heat generation and transport in plasmonic catalysis. So Wouter, do you want to load your presentation?
Yeah, thank you very much, Sasha. And a big thanks to the organizers for giving me this opportunity to present some of my recent research to the community in this way, even though I'm not a member of the reactive plasmonics group, but it's a nice way to talk to you. Emiliano Cortés and also Ruben have been talking quite general a lot about plasmonic reactions, plasmonic reactivity, and how plasmon can influence a reaction. And I will now look a bit more specific on one type of reaction, which is the plasmon-driven or plasmon-mediated coupling reaction. And in particular, I will show you that heat can be quite important in this type of reactions. The reaction I will be looking at has been around for quite a while. It's the reduction of 4-nitrothiophenol, or 4-NTP, as many people or physicists like me know it. And this molecule has the nice ability to basically easily absorb to any kind of gold surface. So even a physicist like me is able to do the synthesis to get the particles on top of, for example, such nice nanoflowers as we have done here. Now, if you have this and you excite the particles by light, then what happens is that two of these molecules start finding each other, start coupling to each other. They do a coupling reaction by forming an N bond, and then you get this kind of azobenzene compound, which is here dimer-mercaptoazobenzene, very much known as DMAB. Now, this is a fairly standard plasmon reaction, basically because it's easy to observe by surface-enhanced Raman scattering. This is the surface spectrum of 4-NTP before any reactivity. And if we now start shining a laser on it, what happens is that new peaks appear. Actually, it's something like 6 or 7, but 2 are very dominant. It's the ones here. And those can be really well assigned to modes of this coupled DMAB molecule. In the beginning, when this reaction was new, there was quite some discussion if it's really a new molecule which is formed here, but nowadays it's actually quite agreed upon. Now, at this point, it's probably a good idea to look at what the plasmon actually can do to make such a reaction happen. And I'd like to discuss this on such kind of an energy reaction diagram, where you just plot the free energy against some kind of reaction coordinate, which shows the progress of the reaction. And then we have the reactants on one side and the products of the other on the other side. Now, to get from the reactants to the products, what we have to overcome is this activation energy barrier. Now, what a plasmon can do on the one hand is it can work as a catalyst, for example, by electron transfer, and mostly by electron transfer. So this means reducing the energy barrier. I know the processes are usually more difficult than this very simple picture. If you, for example, look at the diode process or at the raise of the Fermi level, to be precise, you have to plot it a bit differently. But in principle, it does the same. It reduces the activation energy. The second thing the plasmon can do is it can provide the driving force to get the reaction actually running. And this is mostly done by heat. So heat pumps, the heating, the nanoscale heating pumps energy into the system and provides a driving force to overcome this barrier. And the more heat you have in it, the easier it is. And this is what actually usually chemists do. They make something hot to overcome an activation barrier. If we want to look at this kind of processes, then what we normally do is we make this kind of Arrhenius plots, meaning we plot the logarithm of the reaction rate against 1 over the temperature. And then we get such line type plots where the activation energy is just the slope of the plots. Often actually you see them the other way around. Now, if we have a process where a plasmon catalyzes the reaction, what we expect is that if we increase the intensity of the light, the activation energy will go down. So we get some kind of change in the plot like this. And but to make such a plot, what is important is that you actually really know what is the temperature of your reactor, of the reaction which happens to go on there. And this is the point where we came in and where our research started, what I'm going to tell you in the remainder of this talk. And this is for once how we measured the temperature. We did it with micro Raman thermometry. And a second then, how we can use this temperature measurement to study a reaction, a prototype reaction here, this DMMB formation, and how a plasmon can actually enhance such a tandem type reaction. But let's start with the thermometry. Now, usually if we think about Raman scattering, what most people think about is the Stokes line, right? It's we scatter from the ground state via virtual level to the first excited vibrational state. And we get the Stokes spectrum. But of course, there's also the anti-Stokes spectrum. And the anti-Stokes spectrum is started at the first vibration excited state and then goes back to the ground state. It will measure a photon, which is more energy than the original laser photon that gets into there. Of course, this process is extremely temperature dependent. It depends on the population of the first vibrational state, and that goes with the Boltzmann distribution, where then the temperature dependence comes in. So we can actually calculate via this formula from the ratio of the anti-Stokes to the Stokes intensity, the temperature of a molecular vibration. We went to look if we can actually see the anti-Stokes lines, and it took us optimization, but it is possible. Yes, it's really there. Here, this is the magnification of the anti-Stokes line, so you can actually see it. And now in principle, you can calculate the temperature by this formula. The only thing you have to do before is to get rid of this background somehow. And in particular, in the anti-Stokes case, this background is, however, not only annoying, it can be helpful. And why is this so? This is so because of this process, which was proposed here by the Baumberg group. And it is, if you look at the Fermi sea of electrons in the particle, you can, and the particle is hot, you have a lot of electrons which are actually excited above the Fermi level. And now you can excite such a hot electron, via a virtual energy level. You can scatter it also to a less energetic place, and then the photons, the scattered photons, will have less energy, so they will appear on the anti-Stokes line. And that's exactly what we observe here. So this is the anti-Stokes background for different intensities fitted to the Fermi Dirac distribution. This is different filters we use to get different intensities. And using this, we can now make a plot where we calibrate the temperature towards laser intensity. So we know exactly with a certain laser intensity, this is the temperature our particles have indeed. After having subtracted this background, we can now also measure the Stokes anti-Stokes ratio and see what the molecules actually have what's the temperature of the molecules actually. And we found some interesting things there, which you can very nicely see in this kind of plot. Here we plotted the anti-Stokes line up top of the Stokes line. And well, by just multiplying the anti-Stokes line by this Boltzmann factor, where we use the temperature of this highest NO2 peak, which is from the nitro group of 4 NTP. And then in principle, if everything has the same temperature, we should have two spectra which are on top of each other. And as you see here, for a low intensity, that actually is the case. For a higher intensity, we see two things. First of all, the reaction starts running. So we see these DMAB peaks over here and here. But we also see that the DMAB has a much higher temperature, obviously, as the reactant. So the product has a higher intensity as a reactant. That's quite interesting. It becomes even more interesting if we compare the temperatures we have from the background of the particles to the temperature of the molecules. So here we have the temperatures which we got for the molecular vibrations. Here we have the temperatures we got from the background, the Eddie-Stokes background. And if we now look at low intensities here, we see the particles get hot, they get warm at 60 degrees, but it's quite an increase in temperature. And the molecules basically have the same temperature. That's kind of what you expect. Everything's in thermal equilibrium. However, if we crank up the laser in a way that we start seeing the reaction, then what happens is that the particles even get hotter, so 150 degrees, now it's really hot, but the molecules, they become really hot, or at least the temperature, the formal temperature, which you can calculate from this molecular vibration, is really high. It's 200 degrees for the 4 NTP NO2 vibration and 350 for DMAB. Actually, our explanation for this is that what we see here on the molecules is probably not really a temperature, but rather a result of the injection of hot electrons, that we kind of have a selective vibrational pumping of the molecule, which in the injection of hot electrons, and in this way, the vibrations are more strongly occupied than you would expect just from the temperature. For our temperature measurements, we decided that for the reactivity, it's probably better to look at the nanoparticle temperature, because here you really have a temperature. It's not only a single vibration we look at. Now, having established this temperatures, we can now look again at the rate versus intensity. So we can look how the rate changes with intensity. And we did this by taking this kinetic Raman measurements. So you see here how the spectrum changes just if you shine on with a laser on it and you wait for some time and you measure every second basically. And you see how on the positions here P1, 2, 3, the product peaks appear, and on the positions R1, 2, 3, the reactant, so the 4 NTP peaks disappear. And now we took the P1 peak and we plotted it against time. So this is just the maximum of this peaks, and we did this for different intensities. And as you can see, obviously already from these measurements, the rate goes up. And you can now plot the rate for different intensities and actually have more for different laser powers against the laser power. And you see that this kind of exponential increase that somehow tastes like temperature already. And we said, okay, what is actually now really the influence of the temperature increase we have from the laser? I mean, we know it gets hot. And what is really the influence of the electron injection? And what we were expecting was kind of an activation energy Arrhenius plot, as I've shown you before. I will show you what we got. So this is the rate against the intensity. And then we compared it to an experiment where we measured the rate for different externally applied temperatures with a single laser intensity. And since we now had this calibration, so we could measure the temperature of the particles in situ, so we know how how hot the particles get for a certain laser intensity, we could convert this intensity over here into a temperature and make an Arrhenius type of plot. And what we got was this. Now, actually, the orange bars, orange point dots are again the points we got from the heating experiment, and the other one from the intensity dependent experiment. And as you can see, they exactly show the same activation energy. If you would put just one color, you wouldn't see which one is from what experiment. So this is actually a bit different from what we expected. As I said, we expected a different slope for both measurements. And that was a bit puzzling, but I think we got an explanation for this. And the explanation is as follows. If you do this kind of dissociation experiments, as many people do, for example, with dyes or stuff like this, where you have usually one activation barrier, and that's why you get such a plot as I plotted in the beginning. But for this kind of coupling reactions, it's probably the case, or it is the case, that you have more than one activation barrier, more than one activation energy. The first barrier is the energy you need to actually activate the initial molecule. So it takes a certain energy to put an electron from the particle onto the molecule. This is the activation barrier. This one can be catalyzed by the plasmon, because the plasmon provides energy to the electrons, provides hot electrons, and so on. And so the activation energy in this case gets lower. However, in dimerization reaction, we have a second barrier, which is the dimerization step. We have two intermediates which have to find each other. So they have to bend in a certain way. They have to go to a position which is not thermodynamically ideal. And you first have to produce this position. So you have a second activation barrier. And this one is not catalyzed by the plasmon. So it doesn't change how many electrons are actually inject into the particle. The only thing what helps here is temperature. And now if we're in a situation, as soon as the first barrier is lower than the second barrier, the only thing which we see, which we remain seeing, is the second barrier, is the activation energy from the second barrier. And therefore, the only thing in the intensity dependent of this reaction what we see is indeed this second barrier. And if we measure anything in this on this reaction rate wise, we're always dealing with this dimerization step. Now, with this was a theory to try to confirm it, and we try to confirm it by comparing it to a second type of dimerization reaction from a molecule which is structurally very similar to 4-NTP. It's this 4-NT4-MBM molecule. It's basically the same. The only thing is that we now have a methyl group, which makes the whole thing a bit more flexible. It can move a bit better, and therefore it needs less energy to reorganize. So if you're right, then what should be is that the reaction of this second molecule is much faster, and that's indeed what we observe. So the formation of this DMMA molecule is really a lot faster than the formation of this DMAB molecule. Of course, we did a lot of more experiments here to confirm there's not another way, and we did some DFT calculations and so on, but in the interest of time, I didn't include it here. So what I showed you today was how we measured the temperature, both of molecules and of particles. And that's actually the molecule temperature is maybe, or the vibrational temperature of the molecules is maybe not the best thing if you want to have the reactor temperature. Then I showed you that the nanoscale heating can be a limiting process in plasmon-mediated chemistry. And therefore, plasmon excitations are great because they can not only provide a source for catalyzing a reaction, but they can also provide the driving energy to overcome multiple barriers, and sometimes actually both is important. So with this, I want to thank you for listening, and all people involved, in particular in Matthias Berger's group, but the other people from the University of Potsdam who helped here, and people from Max Planck and Institute and the Federal Institute for Materials Research and Testing helped as well. So thank you very much.
Thank you, Wouter. Very, very nice and interesting talk. We do have one question in the chat. So it states, molecules are on surface and somewhat bonded. Can you please enlighten, I guess, such dimerization upon surface, or it's in equilibration with solvent after reduction? Saikat perhaps can elucidate maybe the meaning of the question a little bit better.
I have an idea. I try to answer it, and if it's wrong, then please correct me and state what the right question was. If I get it right, the question is if the molecules, first of all, if they're bonded on the surface. Yes, they are bonded on the surface, so they to what I was saying in the beginning, they are bonded via this thiol group. And you can be quite sure about this. I don't have it in stock here, but there's actually a Raman signature of this hydrogen sulfur bond. And you can see it disappears, so it's quite clear that it's bonded on the surface. There is no solution around there, so and it doesn't dissolve from the surface. It really stays on top of the surface. How it geometrically is possible that the dimers are formed, that's actually not entirely clear. Because if we compare the DFT calculated Raman spectra of the dimer to what we measure experimentally, then we see that it's probably indeed this kind of cis state. So maybe I don't know so this kind of cis state. So that it's bonded. It has to be bonded in this way. So what we believe is that actually the molecules dimerization mostly takes place in spots where two particles are very close to each other, which would be not really surprising because there are also the hot spots which are more best for electron injection. So that would fit actually there very well. But we haven't, as far as I know, never done it in solution now. Does it answer the question?
Do you want to perhaps indicate in the chat whether or not your question was answered? So intraparticle, does this affect kinetics?
Now, actually, we have measured the kinetics on quite a lot of different substrates and quite also different particle types. And it seems as long as you have it on a substrate, it seems to be quite stable and show the same trends, at least in the kinetics. So of course, if you measure different spots, it's not always exactly the same. As I said, in solution, as we've never tried in solution, and I think in solution, just by having single particles in solution, it's probably not going to work, but it would be a nice experiment to do. But then again, you could do maybe a solution experiment where you have aggregates of particles and you absorb something in between. But then again, it's interparticle, and then the situation is a bit the same. Yeah, question is a bit what you're aiming at there, because
perhaps you and Saikat can discuss this at the roundtable.
Exactly. And we have also new questions, so.
Yeah, well, before that, I believe Julian did raise his hand. So Julian, do you want to ask your question first? And then...
Yeah, please.
Yes. Thank you for the very nice talk. I have a question regarding the fitting of the anti-Stokes signal. Do you consider somehow the shape of the plasmon resonance and the fact that it will be differently enhancing different wavelengths?
Yeah, thank you very much. Very good question. I just had 20 minutes. I didn't talk about that, but indeed, and I think you can see it also here. Yeah, you have to consider the shape of the plasmon. There are basically two possibilities. One is you take a molecule of which you know that there's no electron transfer, and you measure the Sus spectrum, and then you see the different. Then the Stokes and anti-Stokes should have one temperature, right? And then you could use this as an experimental calibration. The other thing, that's actually the way we have done it. The other way I found more recently in literature is people who just divided it by the plasmon resonance spectrum. But then actually not by the absorption spectrum, but you might know you can get a fluorescence spectrum from plasmonic particles. So you can get a recombination. And you have to divide by this recombination spectrum, because that is more or less the same thing, which also excites, what really makes the enhancement, let's say.
Mm-hmm. Thank you. So this was done not on a single nanoparticle, but on
several.
Averaging several. Mm-hmm.
Yes.
Thank you. Thank you so much.
You're welcome.
I have a related question before we move on to the next one. So in previous works, you have shown that you do get a similar thermal rise of the background in the Stokes lines as well. So what is the difference here? Like, I believe your previous works were on nanoparticle systems. So was that the reason for using a thin film geometry in this case to avoid the heating effects?
Oh, and in this case, I mean, actually, we wanted to look at the heating, right?
Right, but this isn't the anti-Stoke.
You mean, now I know what you're talking about. Yes, we have, maybe I have even a slide to it. We have done experiments where we measured the temperature on a completely different way, and by Raman, by Xray spectroscopy, and of course it doesn't work. There we used this kind of substrates, and we measured the X-ray reflectivity for different temperatures, because if you have X-ray scattering, then you measure the distance between two planes, and if you make a particle hot, it gets the planes go further from each other, and you can measure it very, very nicely. However, the problem with the experiments is that the X-ray spots are very big, and so to get the same intensities as you have in a Raman spectrometer, you need to put a lot of intensity onto this particles, and this 10 watts was about the same thing which we had in this very small, this low intensity Raman experiments. Yeah, so you just destroy everything before you really see a good signal. And so since we wanted to have an in situ measurement, so really on the same conditions as we see the reaction, we decided that this X-ray measurements is not the right way to, I mean, you can measure the temperature, but it's not the right way to look at something in a micro Raman setup. And then we looked for another way to measure the temperature, and it works very nicely with this anti-Stokes measurements. So it's.
So I guess my question is more, would the same sort of technique with measuring anti-Stokes work with nanoparticulate films? You know, when you do have like thin film nanoparticles, or would you have to that heating effect from intensity?
I mean, you will have of course you will have a heating effect, a less good heat transport, and it depends a lot on the entire structure you have. So if you do it on glass, of course glass has a very low heat transport coefficient, so it will melt right away. So you should do it on something which, I don't know, at least quartz, or on a silicon substrate or something where you can really dump in the heat and cool it from the back. Then basically you can do it as well. That's
so I guess we could address this last question from Anushree, who asks about how you ascertain the high activation energy of dimerization relative to the
I don't see the question anymore. Wait a second, I have to open the chat again. So we don't ascertain it, we observe it. So the question is how we can be sure, if I see it right, how we can be sure that really the second, this dimerization step has really the higher activation energy. And actually there are two parts on which we do this. One is really the fact that we see the same activation energy. It doesn't matter if we just photo heat or if we externally heat our sample. And that shouldn't be the case. I mean, if I have this activation step as a limiting step, I should have I should see somehow a different light dependent, intensity dependent activation energy. And the second thing is indeed this type of experiments where we build a setup where we said, okay, we have here molecules where the only difference is the flexibility. Actually, it's more difficult to inject electrons into this 4-NBM molecule than into this 4-NTP molecule. So in case the activation barrier of electron injection would be higher, what would be the limiting factor, we would expect in this experiment that the 4-NBM reaction is a lot slower. But on the other hand, what we see is that the 4-NBM reaction is faster. So it's obviously the flexibility of the molecule which is dominant, which is the dominant activation barrier here. And that's how we rationalize that it's probably this two-step process. Does it answer the question? I guess so. I hope so. Okay.
Yeah. Thank you. Yeah, now I get it.
Thank you very much.
Yeah. Thank you.
You're welcome.
Thank you very much, Wouter. Actually, thank you to both the speakers for today. Very interesting talks and a very interesting discussion. And as I previously mentioned, if you do have follow-up questions, do stay around for the roundtable discussion. But I think now we can move on to the posters, the afternoon posters. So Megan, do you want to maybe show us the video?
Good afternoon, everyone. I'm Jeremy from the Optical Nanomaterials group in Cambridge. We've been developing magnesium as a cheaper and sustainable alternative to add to the plasmonic toolkit. Magnesium has an extensive UV visible near-infrared plasmonic range, while also sustaining lower losses than, for example, copper or aluminum. We synthesized the magnesium particles using lithium naphthalenide as a reducing agent and dibutyl magnesium as a metal precursor. This produces a mixture of hexagonal nanoplates, which are the single crystal for magnesium's HCP lattice, and a variety of folded shapes that come from single twinned in the crystal structure. We can then harness the reducing potential of magnesium by making it react with other metallic salts that then produce decorations at the surface of a partially oxidized magnesium core. We study these particles via their single particle optical signature by creating what we see in microscopy with SEM maps. This allows us to compare single particles that have similar either shape or size with or without decorations that can, depending on the selection of metals, be either plasmonic or non-plasmonic. Finally, we've been able to protect the magnesium core using a core shell architectures where we use either silica or polydopamine layers to extend the durability and the stability of these cores either in water or in different solvent mixtures. This opens up a very interesting new avenue for enhanced spectroscopy, for example, with surface functionalization of the shell itself, or with different application of magnesium's plasmonic properties in water mixtures for photocatalysis or photothermal imaging, for example. Thank you for your attention.
Our last work focuses on this question: how hot a nanoparticle is under continuous wave illumination. You all know that when plasmonic nanoparticles are being illuminated, they behave as localized source of energy. Heat is being released to the surroundings, energetic charge carriers are available, and intense electromagnetic fields are built near the surface. All of these effects can be used in different applications that have been discussed today. But disentangling and quantifying those contributions is a challenging task, so we try to quantify the temperature of a nanoparticle to understand its role in our specific application. We did so by using the photoluminescent signal of a nanoparticle, particularly the anti-Stokes component, which has encoded the temperature information. By acquiring a hyperspectral confocal image, that is, making a 2D scan around the nanoparticle while acquiring the photoluminescent signal, we probe it over a wide range of irradiances and temperatures. Then, taking the ratio between any two anti-Stokes signal, we see that the expression contains these temperatures. By using the linear relationship here, we can see that a new expression is found which has only one free parameter, the photothermal coefficient. Then, by fitting all possible ratios between anti-Stokes signals, we can find an average photothermal coefficient for our nanoparticle, and knowing the radiance that we use in our experiment, we can estimate the temperature. Then, we answer our question. After that, we study, can we control the nanoparticle temperature? We found that for gold nanospheres, by selecting the right size, you can control the temperature in your experiment. Also, you can modify the surroundings, although might not be so intuitive. This is the takeaway message. Photothermal coefficient and nanoparticle temperature can be extracted from the anti-Stokes photoluminescence emission by fitting the ratio between any two spectra of the hyperspectral confocal image.
Hello, my name is Anthony Mao. I'm working as postdoctoral researcher at Imperial College London in collaboration with University of Liège in Belgium. And today it's a great pleasure for me to present my work at this new edition of the London Plasmonics Forum. The present research is focusing on new nanostructures and nanomaterials for electrochromic devices used as so-called smart windows in energy-efficient buildings and other related applications. Particularly, the idea here is to exploit the properties of localized surface plasmon resonance, LSPR, demonstrated by specific nanocrystals of highly doped metal oxide for inducing intense and selective light absorption behavior at specific wavelengths, typically in the near infrared, when considering species of, for instance, aluminum-doped zinc oxide or indium tin oxide in view of their carrier charge concentration. Such plasmonic nanocrystals, typically ITO, can be prepared from colloidal chemistry routes with a high degree of precision and control on the final morphology, the size, the shape, the composition, and the dispersion properties of the nanocrystals. These routes can include thermal decomposition reaction under Schlenk line and also solvothermal protocols. These methods will be described with more details in the poster. As a result, you can observe that the processed nanocrystals testify for very characteristic plasmonic features, notably evidenced by optical spectroscopy and STEM yields measurements achieved in collaboration with University Paris-Sud-Orsay. Finally, the ITO nanocrystals can be processed into thin films thanks to wet coating procedures, notably by spray deposition. And once submitted to a suitable bias in an electrochemical setup, the nanocrystals film can provide capacities of near-infrared modulation while maintaining the visible range fully transparent, and this with a high degree of stability and cyclability. Ongoing developments are being currently pursued at Imperial College in the group of Professor Sandrine Uitz focus on the association of pantacene molecular films to ITO nanostructure in a will to provide self-powering capacities of the electrochromic materials and especially the plasmonic electrochromic materials. Thanks for your attention.
Hello world, I'm Sinue and this is my posters video about losses, evanescent polarization and unidirectional coupling in guided optical modes. Our starting point will be this slot, mimicking a lossy waveguide where electric field oscillate and with non-wave vector Km. In the paper, we demonstrate that the polarization of the evanescence tail and losses are really entangled. To see this, we will use the point carrier sphere, in which, for lossless case, the polarization follows a line from the equator to circular polarized light. While increasing the losses, we obtain a tilting in a non-geodesic cardiac-like path. Any combination of the above is encoded in this poster figure, leading to a polarization loss locking, in analogy with the spin momentum phenomenon. This has implication in unidirectional coupling of dipoles in the near field. For a lossless waveguide, emission in only one direction is possible. But when losses are added, the emission is bilateral. Nevertheless, using Fermi golden rule and taking into account the losses, we can retune the dipole for obtaining now perfect directionality. The possible combinations are here, where only diagonal terms shows unidirectionality for the electric slab, but it can also implement in plasmonic interface with the SPPs. But this idea can be also obtained using the angular spectrum of a dipole, looking for null amplitude points in yellow because that direction won't be allowed. Here, the spectral landscape without losses is presented, we found that yellow points, 0, lead to an unidirectional coupling in the opposite K direction. In the lossy case, we can initially see a clear 0, only local minimum. True 0 values is located above, in the axis corresponding to imaginary part of the K vector, giving rise to complex angular spectrum. Location of these zeros in real and arc angular spectrum for lossless and lossy case respectively are included here. Thank you so much for your kind attention.
Hello, my name is Joanna, and my poster is about using plasmonics to characterize memristors. But what is a memristor? It's an insulator sandwiched between two electrodes. A conductive filament is formed in an insulator upon the application of voltage of one polarity and then ruptured by another polarity. This means that the logical on or off state is not lost when voltage is no longer supplied, and then a memristor is in fact a memory and a transistor combined in one device. In a standard computer, up to 80% of energy is used on the data transfer between logic and memory units, and this energy can be saved by memristor-based computers. Sadly, currently, a poor understanding of a switching mechanism prevents commercial utilization of memristors. The switching mechanisms are mostly studied by electron microscopy, which is invasive, destructive, and in vacuum rather than in air, so it's insufficient for finding true understandings. However, we have developed a non-destructive optical technique to observe in situ and in real-time memristor switching under ambient conditions, which is very important. Formations and ruptures of conductive filament are captured within a tiny plasmonic hotspot, which greatly enhances optical signals coming from a hotspot only. This means that the optical measurements can be linked to electrical and material properties of a switching channel. We first proved this method to be successful by investigating memristors based on silicon dioxide, and our research indicated that the filament nucleation position can differ from cycle to cycle. We then tracked alterations in an optical response upon voltage changes in strontium titanite. We concluded that an oxide reservoir at the interface of strontium titanite and strontium dioxide might be the cause of device breakdown upon cycling. Our future plans involve testing memristors, which use two-dimensional materials such as hexagonal boron nitride. Thank you very much for your attention.
Hello, my name's Alex and I'm a PhD student at King's College London. This poster showcases my research in controlling properties of the electric field around a plasmonic nanoantenna using the polarization of incident light, in particular the position of cold spots. These cold spots are regions around the structure where all electric field components are zero because the field scattered by the antenna has cancelled out with the incident light. Cold spots have seen applications in high-resolution spectroscopy techniques such as minflux because electric field zeros are not diffraction limited. It's possible to move a cold spot anywhere in the space around a plasmonic structure in the same way that it's possible to move the nodes in an interference pattern of two or more plane waves by balancing the amplitude and the phase of each plane wave's electric field vector. The presence of a plasmonic structure, whether it's a nanoantenna or any arbitrary scatterer, does not change this fact because of the linearity of Maxwell's equations. By understanding how a nanoantenna responds to different polarization components when illuminated by a plane wave, a linear system of equations can be built and solved to find the amplitude and phase of the plane wave components which enforce a set of conditions. Provided enough degrees of freedom, each component of the total field can be forced to zero somewhere in space, creating a cold spot. We demonstrated that two plane waves are sufficient to move a cold spot along an arbitrary path around 2 point scatterers, which were modelled as coupled dipoles. As it's moved, the polarization of each plane wave maps to a path in the Poincare sphere. Limited only by the precision of the plane wave components, the cold spot is an exact zero and will remain in place even when globally scaling both plane waves by any amount. Thank you for listening.
Hi, my name is Marcian Palma do Carmo and I'm a student in physics at King's College London. In this work, I present a proof-of-principle device that enables the manipulation of sub-wavelength electric particles with minimal effort. As you may know, manipulation of this type of particles can have applications in several research fields, but the techniques that are normally used for this purpose are greatly limited by diffraction, which is the case of optical tweezers, or they rely on the use of very high optical powers. For this reason, here we present a device that is based on plasmonic interactions and that enables the rectified manipulation of the electric bits just by taking advantage of an external optical modulator and of the asymmetries that are present in the system. Essentially, it consists on a set of asymmetric nanoantennas made of gold and chromium and designed to have the electric fields concentrated in the gap of the longest nanoantennas, therefore making this the preferential spot for trapping and guiding the particles. You can see it in action in this animation, where after a period where the particles are undergoing Brownian motion, an external potential is applied in order to trap them in the gap of the closest nanoantenna. If we then periodically turn this potential on and off, the rectified motion of the bits can be achieved. We can also calculate the optical forces and trapping potentials that the bits suffer when on top of these structures by integrating Maxwell's stress tensor over a surface that contains the particles, and therefore taking into account all of the electromagnetic fields beyond the dipolar approximation. From the figures shown here, you can see that due to the system's asymmetry, the fields and forces are continuous throughout the entire ratchet, and they have a clear well on the longest nanoantenna's gap, as shown from the plots on the right that show the optical forces and potentials calculated with the tensor method, respectively. So, to summarize, we have presented a plasmonic system that enables the manipulation of the electric particles with minimal effort, and for the next steps, the ratchet will be fabricated using electron beam lithography, and the controlled manipulation of the particles shall be demonstrated. Thank you very much for listening.
Hi everyone, my name is Romain and I'm a PhD student at Imperial College London. Let me guide you through the research that's been led in our group on time-varying epsilon near zero metasurfaces. These are nanosystems whose properties would drive and change in time on very short timescales near the optical frequency. Our main platform for such experiments is indium tin oxide, or ITO, an ENZ material with very strong nonlinearities thanks to its hot electron dynamics. The usual limitation in efficiency of these nanosystems is the high index contrast at the interface with the medium. We try to overcome such limitation by depositing gold nanoantennas on top of a 40 nanometer thick film of ITO. The plasmonic resonances of the antennas had strong coupling with the NZ mode of the nanolayer, and thus we achieved strong field enhancement and ultra-fast change in properties of the medium with that nanolayers with antennas on top. Now, the main limitation in absolute efficiency of this system was the low damage threshold of the gold nanoantennas. So what we tried to do instead is to deposit an unstructured layer of gold on top of the ITO and start shining from the substrate. So we are now accessing the Berman mode of the ITO, which also shows very strong field enhancement, but we are not burning the gold anymore, and we can explore high saturation physics. This is how we managed to achieve very large changes in reflection, about 0.7, as well as very large changes of refractive index of the order of unity in the 40 nanometers of ITO. So we already have a very compact and efficient system. But also we can now explore some very interesting time-varying physics, such as time refraction and broadening of the pulse. Thank you for listening.
Very nice mix, very nice. Very nice videos. Thank you very much to all. Thank you very much, Sasha, for sharing. Thank you very much to the speakers. So, we're almost on time, actually, almost exactly on time. So we can move to the next point on the program. It's roundtable discussion. And of course, advantage of being online that everyone can be round table. Okay. So please, I encourage everyone to use chat or to raise hand, and if it's quiet, even just unmute and talk. So maybe to start with, I will share screen. I will try to share my screen. Yeah, roundtable discussion. So it's always fun roundtable discussions at the Plasmonics Forum. And we started this tradition from the very first Plasmonic Forum, and maybe I will show you some slides from that discussion, but maybe not, we'll see. But for today, I think it would be great to hear everyone's thought, maybe futuristic thoughts, some more wishful thoughts about where our field goes. And when I say our field, it's plasmonics, nanophotonics, metamaterials, hot electrons, everything which relates to light interaction with like nanoscale objects. Yeah. And so today already we touch upon several things with several questions, and I just put it here. The first was about new materials. What are the interesting materials we should look at? And new types of nanostructures, maybe completely new effects, and we can achieve in nanostructures, and of course new applications. So the floor is open to discussion. And of course, if there are any additional questions regarding presentations that were in the morning or in the afternoon, or regarding posters that were in the morning or in the afternoon, so please feel free to raise these questions or make a comment. Stefan, would you like to start?
Okay, yeah, thanks for the cue. Okay, so we have heard a couple of talks this afternoon, and it was also raised in the morning, the importance of heat at the nanoscale. So maybe I just want to kind of more or less ask like a question at like this point. So what do people think are the best methods to disentangle effects of light, charge transfer, heat at the nanoscale? So we touched upon like a couple of them in the talks today, such as the anti-Stokes to Stokes-Raman technique, direct reaction monitoring. So some thoughts around this, yeah. So like those of you that are very much in the know about plasmonic chemistry will also know that the role of heat is still like a very controversial issue, I think. So if you just think back to our Faraday discussion, I think it was probably the most disruptive opening talk ever that we heard there. So yeah, let me pose maybe like that question. Do we know everything that we need to know on how to disentangle the effects of light, charge transfer, and heat at the nanoscale, or what would be really needed? What would be new disruptive measurement techniques or combination of measurement techniques to achieve that? Or does it
okay. Yeah, Stefan, maybe I can. Oh, look, Leslie's just said the dynamic measurement should unravel those. But I would like to ask a much more straightforward question, and that is that we've been looking at materials that would be able to sustain quite a lot of heat in various plasmonic structures. And I'd like to know where we are with the potential use of heat for destroying cells, for example, cancer cells. Is that still something that we are interested in, or is it something that, I mean, now you're looking at different sort of methods in your new program grant. And I wondered whether we are still interested in generating heat at a very local scale for destroying cells.
It's a very interesting, important question. I don't know if Sasha or David would like to.
I'd comment on Neil's question by saying it seems to me, with another question, which is, it seems to me the issue is more identifying nanomaterials which the body can get rid of afterwards. And often these the sort of nano heating materials that are developed are not suitable for the human body's alimentary canal, or rather the kidneys to dispose of in an easy way. I mean, Sasha may know, because I mean she's working on polymer nanoparticles, for example, as one way round that. I've seen there are other groups which have been looking at ways of so I think there's a program grant between Exeter and Cambridge looking at nanoparticles that can break up, maybe. And a lot of money's going on into this. I don't know if people can comment on where the rice activity has got to now, since they were the first along in terms of commercialization.
So the rice activity, I know that in, I think, summer 2019, they concluded a major study on prostate cancer. Well, a major study, I think like about 50 people or so, on for use of their gold nanoshells of like just the right size so that the body can actually get rid of it on prostate cancer. And at least the press release at that time said that that was very successful.
I think often
I don't know what happened in like the 1.5 years since then.
I think it's sort of shown in a lot of those studies is that the issue not so much the plasmonic material, because they tend to be things like gold, which is really inert for the body, but it's the molecules that are on the surface that are acting as stabilizers, and then the reactions that happen after. So in that sense, if you heat it up to high enough temperature, they burn off, and then that's less of an issue. And the gold of the right size will be able to pass through natural methods. But for any other material system, however, of course, there's just not enough data there, basically. I mean, you need to conduct very, very in-depth studies of how body reacts to these materials, and I don't think anybody will be volunteering anytime soon. And there's just too many of them really to do it on a mass scale. I mean, so, yeah.
And then the thing is important word that Sasha said, it's right size, because in order to use nanoparticles, or depending on material, so you need to optimize resonance for given wavelengths, and sometimes size may not be compatible with safety.
They need to be big enough that they stay in the body long enough to measure or act upon, and then small enough that they pass through things, but not the blood-brain barrier, obviously. So, yeah.
So there was question in the morning, and then there was poster in the afternoon regarding magnesium particles. Magnesium was plasmonic material. So I don't know if Emily is here to comment on this.
No, and he's not there. I could respond to a few questions about that.
Go ahead.
We've been using magnesium just as a plasmonic kind of to investigate different modes, but I guess you're right with regards to the size at the moment. The particles are quite big, and in terms of application, we're still investigating that. So there's a lot of promise, but that's still being tested. I've heard from a few people about the magnesium content in the body, which is typically 300 milligrams, can be accepted. Particles themselves would be, the loading would be quite much lower than that, but at the same time we have some effect about if this magnesium would be dissolved and released all in one go at one spot, then there's a bit of a study that needs to be investigated there.
So if I could, I will rephrase the question which was asked in a way that, are we happy with the material systems which we have already, which we have developed and investigated for the last 5-10 years? And if not, what kind of material we need? So do we need material for a specific wavelength, or we need a material which will be able to structure in some different way. So like to achieve low dimensions or some complicated shapes or structures or whatever. So what's the feeling within the community? Do we have enough bricks to build up this building?
Well, so this question just highlights problems that all enabling technologies have. Yeah? There is no one answer to this question, because depending on application, you need different type of materials, different structures, etc., etc. Yeah, and so I think plasmonics now is at the stage when we pretty much understand most of the basic properties, and if we want to go to kind of practical applications, that we need to take very specific application and then take various knowledge that we have now to build kind of ideal plasmonic tool, device, nanoparticle for this particular application, because I don't think there is one size fits all in this.
Oh,
in this.
No.
So this exactly, I think that the field should start looking at particular applications where this all knowledge can be applied to. So from this point of view, like refractive particles, so as we know, refractive plasmonic materials, it's hammer application, this bio application. So there are different application using the same the same property. However, they require completely different approaches, completely different designs. Okay. So what about new materials? So we discussed a little bit, so we have some interesting possibilities there. So what about new types of nanostructures? Can we do something beyond nanoparticle, nanoshells, bow ties?
And I don't know, it's just an idea that came to me, but I think the sort of the interface between plasmonics and maybe self-assembled methods hasn't been quite explored to its fullest yet, and mostly in the field of self-assembled metamaterials, maybe, where I think we can get a lot more structuring achieved with the new assembly methods that are appearing recently, both like such as convective and capillary assembly, for example, but then using nanoparticles as building blocks. And then somehow shelling that and removing into solutions. So it'll provide a way to essentially produce colloidal metamaterials that are built from very, very small particles. And perhaps that will give us yet another way to control the mode profile, basically, of these particles. And yeah, I feel like there's still some things left in the self-assembly sort of aspect of things that we could do.
Anatoly, if I can, there's also a lot of room now for new method to design nanostructure, method that come from machine learning approaches or adjunct methods. I have a feeling that all the nanostructure we use so far, the majority are very intuitive. Like a disk, it makes sense. It's the simplest geometry. A bow tie is, again, a hotspot. We haven't gone much beyond that. For some application in particular, for example, for single emitter control, I think we have a long way to go. So I bet the new nanostructure that there is a lot coming there.
So single emitter control, you mean like combining like quantum dot or molecule to?
Yes, exactly. To nanostructure.
So where are we now in this field?
I think there's a lot of activity with new methods, which design structure which are fairly different than just a simple bow tie. Structure that are more resembling the dipole, for example, if you are optimizing on a dipole, so which has lobes. And I think that there's a lot of activity on the blind approach, let's say the machine learning approach, where looking for some pattern using general symmetries or so, or the adjoint method, for example, it's more based on the field coming from the dipole. This has more physics, but of course less explorative than the machine learning. I think the limit is what we can fabricate. So it's always nice to design things, and but I think we are getting better at that as well. So I would bet that we will go beyond the dimer to something a bit richer. Especially if you want to go to a higher order. For example, if you want to make an antenna for a quadrupole, then it's not a dimer anymore.
Yeah. So the problem not in this, as we saw in different circumstances, even so, as soon as you start including like magnetic dipole, quadrupoles, so then going from spherical geometry to disk is also not very straightforward, because it's just completely different behavior. Yeah. Any other comments from somebody outside reactive plasmonics? No, everyone is very quiet. So what about new effects? So as I said, until like 5-6 years ago, nobody thought about hot electrons, and hot electrons appeared. So what will be next? It was field enhancement and hot electrons. So what is next? What is new plasmonic effect on horizon? Would you like to say something?
That was the idea, if I may. I became quite interested in plasmon-induced charge transfer, so plasmon-induced direct charge transfer. I don't know if you know this recent experiment by the Cerulo group, where they had a cadmium sulfide nanorod with gold nanoparticles on top, and could show that there is a direct charge transfer excitation from the cadmium selenide, it was actually, to the gold particles, which is a lot more efficient than that you first excite some electrons and make them hot and then transfer them, because you then have a massive loss. So that's, for me, even though it's not an entirely new effect, but something which is not really understood and not really well developed yet.
Yeah, it's a very interesting subject. So I think if anyone thinks about some new effects, they don't want to tell anyone else, right?
And this one is published, so.
Yes, I know.
That's not mine. So.
Well, what do you think, Anatoly? Turn it around.
Well, if I would know, I would tell you. And new applications?
I think that there's something that was mentioned at some point today, and I think it's something interesting for many applications. It's the role of interfaces. So I feel that we know a lot now about the plasmonic materials itself, but we know a little bit less on how to use that, right? So how to use that heat, how to use that energy, how to use those electrons. So I think that interfaces may be like a good way of getting profit of all these things, right? At some point.
So can I turn this question a little bit, look at this from a little bit different side? So if you're a molecule and you're coming close to the interface, so do you see interface or you see something else?
Yeah, well, I think there is also there is also something else, and it's that the chemical bond by nature, it's atomic in size, right? So if we are like thinking on tracing atomic bonds or like affecting chemical bonds or like molecules, then we need to go down all the way to the atom scale, right? And I feel that's also kind of like maybe a bit of the future move for our field as well in regards to of combination of plasmonics and chemistry, right? Like the ultimate limit should be like the atom size when speaking with molecules or like chemical bonds.
Yeah, exactly. So I remember a couple of years ago when Jeremy Baumberg was studying these small gaps between nanoparticle and thin films. So his example was that in this gap, actually, what you see is not interface, but you see like kind of like soup of atoms, gold atoms, because at this scale you have to already take into account like motion of atoms, and so there is no kind of real interface, or at least interface in sense like rigid interface.
With the question of interface, do we come full circle back to Stefan's opening question, which I'd still like to hear an answer to, which is about disentangling heat and charge transfer. And I suppose my question is how important the interface is with all of that, you know, the local microstructure and how much of an effect that has. But the question that Stefan posed, which I'd be interested in, is how do we tell the difference?
Wow. Stefan, do you have an answer?
Yes.
Well, I think it depends. It depends very much on what you actually study, right? I mean, Emiliano can maybe comment from like the chemistry side. I think you are very well plugged into the controversy that was raised around the first Hallas experiments. So do you maybe want to comment on that briefly?
I think it's a really tough times because it's nearly impossible to have one or the other effect, right? So they are always both present, and when you want to maximize one, you end up maximizing the other one as well. So it's really difficult to kind of like get rid of these things. But I feel that there are some quite nice experiments that show that both possibilities could contribute, right? So in Wouter's talks this afternoon, we saw this, I think, and there are many examples. I think that the clearest examples that some hot carriers can participate in processes, I think it's due to the usage of hole scavengers or electron scavengers in the reactions. So when you add something that can oxidize or reduce easily, and then affect the reaction rate. So that means that there is some kind of like electron transfer being involved in the reaction, right? And then for temperature, I think what Stefan asked, it's also a central thing for the future, and it's that we don't know much about temperature in the nanoscale, I think, or I feel. And I think that new methods should be at some point like developed in order to trace like not only the temperature, but also the temperature profile of around these nanoparticles, right? So how much the diffusion or many other things change around heated nanostructure.
Yeah, yeah. There's actually, I mean, like there's some like really nice work already now, at least probably 10 years ago or 12 years ago by Javier Garcia de Abajo, for example, who very, from the theoretical side, very diligently looked into the problem of temperature at the nanoscale, and I think like a lot of that work actually merits now probably going like back to and re-examining now that experimental techniques have been developed, as we saw this afternoon in the talk, for example, to actually do real like experiments looking at temperature on that scale. Yeah.
Which then comes up is always how you define temperature.
Exactly. So like that's what
it's not so easy. Which part? What's the temperature you have there now? I mean, it's kind of a molecular vibration which is excited, but that's not really a temperature. So that
caused us a lot, not of confusion to us in how to define what is temperature there.
So how did you define it?
Sorry. I was just going to say, and presumably how many molecules and exactly where they are. Yeah. Yeah, indeed.
Okay, so unless there are any other comments, anyone else wants to comment on any of the topics that we discuss or raise another question, topic?
There's another question for you, Anatoly, in the chat on the future. Do you see it? Do you want to take a first step at answering?
Just a moment. Okay, I see from Neil. Okay, apologies, Neil left us.
At the very bottom.
The very bottom.
The fine view of reactive plasmonics. Thanks for the praise, Anthony.
Oh, hi, Anthony. Yeah, so those who don't know, Anthony was part of Active Plasmonics Program grant. Yes. Yeah, thanks for the question. Yeah, so plans for the future, try to continue along the same lines, try to find new effects, as we said. And as we have seen from the presentations today, from all presentations in the morning, in the afternoon, as well as from kind of summary of results of reactive plasmonics. So within this program grant, we identify kind of several different directions which are interesting to explore. And in particular, it's like sub-band gap photodetection, like photocatalysis, or nonlinear optical properties, in particular with like new type of materials like ENZ materials. And I think each of these should be explored further, because program grant, as I always said, the goal of this program grant is a basic research to find some new effects, and then now we know a little bit more about these new effects, then we can take it further to study them in more details, and then to hopefully to some good practical applications. So I think these three directions, at least from my point of view, would be most promising to look at further. Okay, so we have a few minutes left. So Anthony, so if you're still with us, maybe you can tell us something from your perspective, from startup perspective.
Hi, Anatoly. Yeah, it's been a journey for sure. We are sort of raising funds now. We're at a stage of the company where we've got a first product in mind, and yeah, we're trying to raise a Series A fund, which is, it's a different beast, but it's the same as you trying to raise grant funding, I guess. But it's a different world, the commercial world.
So which is easier, commercial or academic?
I don't know. They're equally challenging in different ways, aren't they? Yeah, it's all about going out and pitching your idea. It's a bit like being in Dragon's Den.
So do you enjoy it?
Yeah, no, it is different, but I do enjoy it. Yeah, I never really had any sort of, I guess, desire to go into the industrial world, but you know, it is fun and it's interesting, and you learn something new every day.
Great. So Anthony was speaker at the very first Plasmonic Forum, maybe even first speaker on the first Plasmonic Forum.
Yeah.
Great. See you.
It was a long time ago. I look back at the pictures and I look very young in it.
All right, so I think everyone is waiting for prizes. So maybe Nina, if you would like to announce where we are with prizes, poster prizes.
Of course, very happy to do so. But before we delve into the prizes, I think it's like almost every year, it falls to me to thank Anatoly and Stefan, as well as Megan, to bring us together for, I believe it's the 6th time now, 2nd time virtually, and we're still hoping once again for in person again next year. Fingers crossed, it's actually going to happen this time. And well, the regulars amongst you will know that Rachel, Anna, and I have been sort of the go-to jury for the poster prizes for the last few years, and we were also we're also awarding the prizes today. So we had a little chat about the posters this morning, and we have found our 2 winners, because today we have 2 prizes. One for the morning session on the reactive plasmonics posters, and one for the afternoon session on the general Plasmonics Forum posters. I'll let you know who it is in a second. I just want to add one thing, because people sometimes wonder why people win. So the things we took into account are really everything we had to hand. So that is the science and the poster, but not only the science, it's the presentation of the poster as well as the talks. So all these 3 things together made up our judgments, and this time we actually needed to discuss who the winners are, although we did have similar preferences. So without further ado, for the reactive plasmonics session, I'm very happy to announce that the winner of the poster prize is Ming Fu from Imperial College for his poster entitled Directional Enhanced Raman Scattering Coupled Plasmonic Waveguide with Near Unity Coupling Efficiency. And let me quickly share my screen so you can actually have a look at what the poster looks like, to remind yourself what this is about. Hope I'm sharing the right one. So congratulations, Ming Fu. Megan will email you later with official congratulations, as well as a voucher as the official poster prize. Can we have some applause for those who are not muted?
Thanks a lot. So do you need me to say something about that, or I'm really happy? So thank you so much. It's really my honor to receive this prize. I'm super excited to. Yeah.
Congratulations.
Thank you. Thank you.
And for the afternoon session, so again, that was the general Plasmonics Forum session. The winner is Joanna Siminovich from University of Cambridge for real-time in situ optical tracking of memristor switching. This was her poster. Joanna with us still? I know she was here earlier.
Oh yes, I am. Thank you very much.
Congratulations.
Thank you, I'm so excited. Please email me if you have any further questions about the poster. I'll be happy to discuss. Thank you.
Maybe somebody else does. Well done. So for you as well, Megan will be in touch with official congratulations and a little prize, which I believe is an Amazon voucher.
Fantastic. Thank you very much, Nina, and thank you very much, Anna, Rachel, and congratulations to both winners. I think there's fantastic posters and very exciting science on these posters. And I'm sure, as always, but I'm sure these areas will go forward, and we will hear about these areas maybe from Joanna and Fu on the Future Plasmonics Forum. But thank you very much, Nina.
Thank you again. And I don't know which of you is doing the concluding remarks, but over to Anatoly and Stefan.
Stefan, would you like to conclude remarks?
So I think, well, what is there to say? So I think we all had many Zoom workshops and conferences probably over the last year, and I actually promised myself to limit it very much. But I think today was really like an example where it was very enjoyable, at least for me. I hope for you like as well. I think we had a very good mix of speakers, of styles of presentations, very exciting science. It was also, I guess, a bit emotional for us seeing reactive plasmonics come to an end. So it's 12 years now since we started the collaboration. Anatoly at that time was still in Belfast. So yeah, we have all aged, but I think we managed to do quite a lot of interesting science. We had many good people come through all of our labs, I think. Yeah, so thanks also to EPSRC for giving us the flexibility to do that. And one lasting part of it are these London Plasmonics Forums, which I think actually we are at the 7th now, right?
No, it's the 7th.
Yeah. I was trying to count. We are in year 7 now, and it's really nice to see. Well, so many of you here. So now, obviously, just on the screen, but we will continue with this in the future. I think there's many more exciting topics to come for plasmonics. We have hopefully seen some of the seeds of those today. And yeah, it was a Zoom session that actually, at least for me, didn't feel very long, and I think that's a very good sign. So thanks to all of you for having been there. Anatoly, you have the final.
And thank you very much, Megan, for all your help with helping to organize this. Thank you very much. So at the end, thank you to all speakers, to all poster presenters, and to everyone who attended. Thank you very much, and see you next year. This time definitely in person.